All right, students, welcome to week 13. So we only have 3 more classes after this, so let's hop on in. So if we look at our dashboard here, here's our normal front page. If we follow our link to module, or to this week's module, which is week 13, it will take us to our familiar 4 sections here. The first one being our discussion board. Remember, these are a required portion of the class. They do go towards your grade. So this is just a video on echolocation because this week we are talking about sound waves. And so you watch this short little video, and it's actually very interesting if you're ever curious on how bats use sound to sort of locate food sources and sort of map their environment. It's pretty interesting. So that's the first part of your work this week. Now, the second part, obviously, is our CK12 work. So we have the link to it right here. So I'm going to link out to it. And you'll see, actually, let me make this available to all of us now. So here we go. We're going to set a due date on this of the 26th, just because we are getting close to the end of the class. So we do need to have due dates on those. So there we go. So we got sound waves for week 13. And if we look here, we have 3 short sections just on what is a sound wave, how fast is the speed of sound, as well as the Doppler effect. And then we have a sound wave quiz. So it's your traditional, we just have 3 sections and then a quiz. So nothing too strenuous or too over-involved. It's just these 3 simple sections and then our quiz. So let me hop on back to our unit. If we hop on back to our module here, we have our PowerPoint with no lecture, and then this one will have this lecture with it. So I'm going to go right to the lecture here, and we're going to begin. So we could try to make this a shorter video. One of the things, actually, let me hop back to these sections here. One of the things I really have to impress upon you or really recommend to you are these videos. Because they do a lot of good work at showing you some of the stuff that's in the adaptive practice, as well as working through some problems, sometimes the exact same ones that are in the adaptive practice. So don't skip out on those videos. They're very important. All right. So if we're talking about sound, we want to know what causes sound. And all it is just vibrations. We've been talking a lot in this class about vibrations and different types of waves. And so with sound waves, it's just the vibrations that are caused that create that sound. It's the conversion of it into a different form of energy. So if we talk about sound waves in the air, what we're really talking about is air being compressed and then sort of retracting and then being compressed again and then sort of spacing back out, which are called rarefactions. So we have these compressions, and then the rarefactions make up our sound waves. So the molecules in the air vibrate, creating these compressions and refractions of the air around it. And then we call the frequencies from a rare frequency, which is how many cycles per second, how many waves pass by a given point in a certain amount of time. We call that frequency the sound of the pitch. I'm sorry, we call it the pitch. So right there, we call the frequency of sound the pitch. So the higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch will be. So we want to talk about longitudinal waves versus transverse waves because this gets into our reasons for sound. Let me get rid of that. I apologize. So longitudinal waves, you want to think of them of a straight line and an up and down path. So if you think of longitude on a globe, it runs like up and down. And so we're looking at waves that sort of go in that straight up and down sense, as opposed to transverse. So longitudinal waves may be straight up and down, transverse would be the other way. So longitudinal waves propagate through a fluid. Now, we've talked about fluids before, and air is a fluid because it flows. You can have air movement, same way that you have fluid movement, like in water or any sort of liquid. But so we do consider air to be a fluid. And so the reason that they propagate through these fluids is because they're able to contract. So we're going to talk in a slide here about what if you didn't have a medium in which we could contract or expand. So they rely on pressure forces. And so if you think of a slinky or like an accordion, it's the same way. So that slinky, if you make that compressional motion or of one end, it'll propagate all the way through the slinky. And so you want to think of sound waves in a similar fashion. So just a couple of the fundamentals of the sound waves. So we said that they are longitudinal waves, and we are dealing with frequency once again and the wavelength. So the frequency just being the number of waves passing by per second. And so now, before, we thought of them, as the electromagnetic waves before. Now we're thinking of them in terms of pressure. So the wavelength, which is the distance between each successive region of high or low pressure, comes into play when it comes to sound waves. So the frequency, like we said before, is going to be related to pressure, and the higher the frequency, the higher the pitch will be. And that's just because there's so many waves passing by, in a single second. To where if we slow down that frequency and the pitch drops, we have longer wavelengths. So they have that relationship. And so in regards to the speed of sound, because you're going to see some of this in your CK12 work, so the molecules of the medium collide, allowing the wave to be transmitted through it. Once again, think of that slinky or that accordion, or go back to that first graphic that showed the compression and the refractions. And so the speed of sound depends on the elasticity of the medium, meaning that the speed of sound in air is much different than the speed of sound in water, which is much different than the speed of sound in another liquid. Similarly, when we're talking about the speed of sound like in air, if you've ever seen the videos of like someone inhaling helium and their voice gets really, really high, well, helium is less dense than air. So therefore it travels much faster through it, and we have a higher frequency and a higher pitch. If you've ever seen anybody like with a balloon, suck in, it's called sulfur hexafluoride. That's much more dense than air. And so it will drop the frequency very much, and you get a much deeper voice because it's traveling much slower through that medium. And so the more elastic the medium, the faster that the sound will be. And the elasticity is just the ability of a solid to return to its original shape after external forces have been exerted on it. So how well does it return to its normal shape? And that will be what determines the speed of sound through an object. So don't pay any attention to the 16.6 for more. If we were in a classroom with our textbooks, that would be where we'd find this stuff, but we don't need that right now. So the medium, when we talk about a medium, we're talking about either air or liquid or anything like that. So now the question is posed, what if there is no medium, like a vacuum? And when we say a vacuum, we mean all air has been taken out. So if you ever heard the phrase, no one can hear you scream in space, it's because there's no medium, there's no air. Therefore, there's nothing for the sound waves to travel through because there could be no compression and refraction. So waves in a different medium or media, if it's multiple. And so if you think in which medium would sound travel faster, steel, wood, or you, think about how well something can be elastic. And so what does the speed of sound depend on? The medium. And so steel does not really have many elastic properties. Wood has a little bit more give and can return to an original shape. And then you think of you. If you if you've ever been hit in the gut, I don't know if you're like me, and maybe so I'm a little chubbier. So if I get hit in the gut, there might be some wiggles there, but it'll return to its normal form, and therefore I have more elasticity. But so that's what we're really looking at here is that it depends on the medium through which it's traveling through, and the elasticity of that medium will determine the speed of that sound. So after you watch the video, you're going to know a little bit more about echolocation, and that also relates to sonar. So what happens with sonar and such is that there'll be sound waves that are emitted. They will bounce off of a certain target and return to some sort of receiver, which can then image it. So the amazing thing is that bats do this as they're flying through the air. So they let out these sounds that will either bounce off of the environment or bounce off of certain prey around them, like flies or other bugs or something. And then as it comes back to them, their brain is able to put together an image of the surrounding area. It's almost like mapping the area and mapping what's in front of them. That's an amazing power. And you can see this is a way in which it's done. You send out the sound waves, it hits the target, bounces back to a receiver, and you can image it based off of that. And you can also tell the what you're looking at based off of how fast it's going to come back at you. That's how a bat can tell the difference between, say, like a leaf and its prey. The elasticity of it between if there's like a wall there, that sound is going to come back in a much different way than if it's coming off of a prey, like a bug or a moth. A lot of moths. So when we talk about sound intensities, like how intense a sound is, we use this unit called decibels. So if you ever heard the term decibels, it's a measure of the intensity of sound. And so if you were able to get near total silence, you could have 0 decibels, meaning that there'd be no sound whatsoever. This is very, very hard to achieve because there's typical, sounds in everyday life. And also if you try to isolate yourself, there's still like the movement of air, which sometimes you can hear, through the pressure in your eardrums. And if we go up here, so a whisper is about 15 decibels, the lawnmower about 90, iPods at full volume get to be about 100, and then a jet engine is 120 decibels, and this is about our threshold for pain. This is when sound actually begins to cause physical pain. And then a gunshot or a firecracker could be at 140 decibels. And so we don't need to worry about the math too much, but the rule is that each 10 decibels is 10 times the intensity of sound. So therefore, if we took the gunshot and total silence, so total silence being at 0 decibels, gunshot being at 140, 10 to the 14th would be, quite a huge number. But that would be 10 to the 14th times the intensity of the sound. And so the sound level would be 2 to the 14th, or 16,000 times greater. So we don't really need to know much about like those getting these numbers, but just know that each 10 decibels is 10 times the sound intensity. And that this makes the sound that much greater, and that's why some sound can actually, damage our hearing in our ears. So that 120 decibels of, so this is an FA-18 Hornet, so a very, very powerful jet. And you'll notice that these gentlemen out here obviously have to wear, ear protection, because the decibels coming off of that jet engine are enough to cause physical pain and hearing damage. And so there's also ways that we can abate the noise, meaning like bring it down. So the automobile muffler. So as the inlet is coming in, we have the resonant chamber, and as it's going through these perforations, it allows some of that energy to escape, and therefore the outlet makes it not as loud as it could be. So you can always like sort of hear when somebody has like a muffler problem because the sound might be a lot more intense. Some people intentionally, alter their mufflers and whatnot to make a higher sound. Don't know why, but sometimes they do. Just different things for different people. And so, have you ever heard of the noise canceling earphones? You might be like, how can they cancel the noise? Well, what they do is they emit a wave, like a sound wave, going outwards, and it will interact with sound coming inwards. And so what happens is when those two compete, it's almost like a big high and a big low meeting, and it cancels it out. So if you see down here, these sound waves that are meeting the ones coming out from the headphones, they kind of balance each other out and cancel each other out here, which provides the silence within the headphones. So it's a pretty cool technology. And so with sound levels, with loudness being measured in decibels, don't worry about the page 47, we don't have our textbooks, but normal breathing, as we're going in and out, is about 10 decibels. And then if we go up from there, the speech that you're hearing right now will depend on the volume that you're choosing to, but just in my apartment as it is about 60 decibels. So when you get to a concert and you could hear, how loud the sound is, you're coming in at about 115 from those speakers. And then the pain threshold is 120. So even at a concert, you're approaching that pain level sometimes. And if you've ever been to a really loud concert, you know that. Sometimes it's just hard to hear. Or you could feel like the bass pounding in your chest. That is a sound wave, hitting you. And so a lot of times, so I've been to a few concerts where I've been able to be like backstage and whatnot, and I always have to wear ear protection because that sound gets so loud, it's almost painful, but it can also cause hearing damage. So The last thing we'll talk about is the Doppler effect. And so the Doppler effect is a pretty cool thing. And you may see on the news when they do like weather, they're doing like the Doppler 5000 and whatnot. Well, the Doppler effect just comes from what's known as the Doppler shift, which is the change in sound frequency due to the relative motion of either the source or the detector. Now, so this as a passing car, let's think of a passing motorcycle, like those Harleys that can get revved up really high. Or think of like an ambulance or a fire engine siren. If it's a mile away or so, you can maybe hear it, but as it gets closer and closer, that sound becomes much more intense because the distance between you and that whatever's making the sound is getting shorter and shorter. Therefore, the frequency is changing, which changes the as the frequency changes, it's going to change the pitch of the sound as it gets closer to you or further away. So, as something is moving towards a certain object, that distance between them is getting shorter and shorter, and that is changing the frequency due to the relative positions. So, the Doppler effect refers to the change in frequency when there is relative motion between an observer of waves and the source of the waves. So when they show the Doppler 5000, like radar stuff, what that's doing is it's sending out a signal that is hitting, whether it be like clouds, rain, different types of weather phenomenon, and then coming back to its original source. So they can see how clouds are approaching based off of the change in the frequency between it hitting the weather phenomena and coming back to the receiver. And so this hopefully will work for you. I don't think this link works anymore. It was a site that I had that no longer was operational. I tried to find another one, but I don't think the link worked too well. But the Doppler with sounds, I mean, if you just listen for the next time you hear like sirens, as they get closer to you, that sound intensity increases. And as it goes further away, it decreases. So that is the lecture for this week. I tried to make it short and sweet. Make sure you're watching the videos. Make sure you're doing the CK12 stuff, reading the articles, and doing the adaptive practice. Alrighty, I'll see you tonight. Have a wonderful time, I guess.